4,000 years ago, before electric lights erased half the cosmos from human sight, a Babylonian astronomer climbed the steep steps of a ziggurat. The night wrapped around her like black silk, and overhead stretched a tapestry of light so dense she could navigate by its patterns. Every star had earned a name, a story, a place in the great clockwork of heaven. She knew them all. But 5 lights troubled her sleep, while thousands of stars held their positions night after night, year after year. These 5 wandered. They moved with purpose, but no pattern she could grasp. Sometimes they raced eastward against the stellar backdrop. Sometimes they stopped, reversed direction, and traced loops in the sky like cosmic scribes writing messages in a language she couldn't read. The Greeks would later call them planets' wanderers, but to her they were simply the great mystery that separated the known from the unknowable. Here's what's really happening. She was watching worlds like our own, following their orbital paths around the same sun that warmed her face each morning. But that understanding lay 25 centuries in the future. All she had were questions burning brighter than the stars themselves. Halfway around the world, Chinese court astronomers faced the same puzzle with characteristic precision. They tracked the wandering stars so carefully they could predict their positions years in advance, creating charts of stunning accuracy. They knew that what they called the fire star, we know it as Mars, took approximately 687 days to complete one journey against the stellar background. They mapped its retrograde loops with mathematical elegance, recorded its brightness variations, and used its position to set calendars and plan ceremonies. Yet prediction without understanding gnawed at them. They could tell you exactly where Mars would appear on any given night, but they couldn't explain why it moved at all. The question burned like incense in their observatories. What makes some lights dance while others stand still? Every culture that looked up asked this same question in their own way. Aboriginal Australians had watched the night sky for 40,000 years, longer than any other continuous civilization. They saw the emu in the sky, the dark dust lanes threading through the Milky Way, and tracked its seasonal journey across the southern heavens. Their songlines connected earthbound landmarks to star patterns, creating maps that spanned a continent. But they too noticed the wandering stars, the ones that didn't fit the eternal patterns passed down through countless generations. In the Americas, Mayan astronomers built observatories that rivaled anything in Europe or Asia. From the Caracol at Chichen Itza, they tracked Venus with obsessive precision, discovering that it takes exactly 584 days to complete its cycle from evening star to morning star and back again. This cycle became sacred, woven into their calendar systems and used to time wars and coronations. They knew Venus so intimately they could predict its appearance decades in advance. But knowing when didn't answer why. The Maya watched Venus disappear behind the sun for 8 days during inferior conjunction, then reappear as the morning star. They saw it brighten and fade in perfect rhythm, yet they couldn't explain what caused this celestial clockwork. Was Venus a god following divine laws? A cosmic mirror reflecting the sun's light? The questions multiplied faster than the observations that spawned them. Greek philosophers, with their love of logical reasoning, tried to solve the puzzle through pure thought. Aristotle imagined the wandering stars attached to transparent crystal spheres, each nested inside the others like cosmic Russian dolls. The spheres rotated at different speeds, he argued, carrying their embedded stars through the complex motions observers recorded. It was elegant, mathematical, and completely wrong. But here's the remarkable thing. Aristotle's model worked for prediction. You could use his crystal spheres to forecast where planets would appear, even if the underlying explanation bore no resemblance to reality. For nearly 2,000 years, astronomers refined sphere models, adding epicycles upon epicycles to match increasingly precise observations. The mathematics grew impossibly complex, but the fundamental question remained unanswered. Why do some stars wander? Aristarchus of Samos came closest to the truth. Around 250 BCE, this remarkable Greek astronomer made one of the most audacious proposals in human history. He suggested that all the wandering star puzzles would vanish if you moved the sun to the center and let the Earth join the dance. Think about it. If Earth orbits the sun, then Mars sometimes races ahead of us in its orbit, while other times we overtake it from the inside track. During our overtaking phases, Mars would appear to move backward against the stars, exactly the retrograde motion that had puzzled astronomers for millennia. Venus would show phases like the Moon, growing bright when its day side faced Earth and dim when it turned away. The wandering stars weren't wandering at all, they were worlds like ours, following predictable paths around a central fire. Aristarchus even attempted to measure cosmic distances using nothing but geometry and courage. During a half moon, he reasoned, the sun, Earth and Moon form a right triangle. By measuring the angle between the sun and moon at this precise moment, he could calculate how much farther away the sun lay than the moon. His measurement was off by a factor of 20. The angle was too small for his instruments to measure accurately, but his method was flawless. He then used a total lunar eclipse to determine the moon's distance. As Earth's shadow crept across the lunar surface, Aristarchus timed how long the moon took to cross the shadow's edge. Knowing Earth's diameter and the shadow's width, he calculated that our cosmic companion orbits 240,000 miles away. Modern measurements put it at 238,900 miles. His error was less than 1%, but Aristarchus's sun-centered universe found few believers. It required Earth to hurtle through space at enormous speed, yet no one felt this motion. If Earth truly orbited the sun, nearby stars should shift position slightly as we swung from one side of our orbit to the other, stellar parallax, as astronomers call it. No such shifts were detected, leading most scholars to reject Aristarchus's radical idea. They were wrong about the cause but right about the observation. Stars do shift due to parallax, but they lie so incredibly far away that the shifts are microscopic. The nearest star beyond our Sun, Proxima Centauri, shows a parallax angle of less than 1 arcsecond, the apparent width of a quarter seen from 4 miles away. Greek instruments couldn't detect such tiny motions, so they concluded Earth must be stationary. Meanwhile, Islamic astronomers during the medieval Golden Age pushed observational accuracy to new limits. Al-Battani refined measurements of Earth's orbit so precisely that his calculations of the year's length was accurate to within 2 minutes. Ibn al-Haytham, known in the West as Al-Hazan, questioned whether crystal spheres could actually exist, since they would need to intersect and pass through each other to produce the observed planetary motions. These scholars mapped over 10,000 stars, catalogued their brightnesses, and tracked subtle changes in stellar positions over centuries. They built astrolabes of breathtaking precision and created trigonometric tables that wouldn't be improved for hundreds of years. Yet they couldn't answer why stars twinkled while planets shone with steady light, or why comets appeared without warning like cosmic ghosts, trailing luminous hair across the sky. In India, mathematicians calculated eclipse cycles stretching millions of years into the future. They understood that eclipses resulted from precise alignments of sun, earth, and moon, and they could predict these alignments with remarkable accuracy. Aryabhatta proposed that Earth rotated on its axis to explain the daily motion of stars, an insight that wouldn't reach Europe for another 1,000 years. But prediction, however accurate, wasn't explanation. Indian astronomers knew when eclipses would occur and how long they would last, but they couldn't say why the moon sometimes turned blood red during Earth's shadow, or why the sun's corona blazed like silver fire when the moon covered its disk. Every culture developed its own cosmic mythology to fill the gaps that observation left unfilled. The Aztecs saw the Milky Way as a cosmic tree whose roots touched the underworld while its branches supported the heavens. Norse mythology placed the galaxy in the realm of the gods, a bridge connecting different worlds. Australian Aboriginal cultures saw it as a river in the sky where ancestor spirits travelled. These stories weren't failures of understanding, they were profound attempts to make sense of phenomena that lay beyond the reach of available tools and methods. The mythologies revealed something remarkable. Every human culture that looked up felt compelled to find patterns, to seek explanations, to transform the mysterious into the meaningful. But perhaps the greatest mystery escaped notice precisely because it was so obvious. Night after night, ancient astronomers gazed upward through darkness punctuated by points of light. They mapped constellations, tracked planetary motions, and predicted eclipses. Yet none asked the most fundamental question of all. Why is the night sky dark? This seems trivial, even silly. Of course, the night sky is dark, the sun has set, leaving only distant stars to light the cosmic stage. But here's what's really happening. If the universe were infinite and eternal, with stars scattered throughout infinite space, then every line of sight from Earth should eventually intersect a star's surface. The night sky should blaze with the combined light of countless suns, bright as day even at midnight. Ancient astronomers couldn't know they were staring at a puzzle that would take 2,000 years to solve, one that would ultimately reveal the universe's deepest secret. It has a beginning, and therefore an age. The darkness between stars wasn't empty space, it was time made visible, a cosmic clock marking the moment since creation itself. The wandering stars that had puzzled Babylonian astronomers were indeed worlds like ours, but the implications stretched far beyond planetary motion. If Earth was one planet among many circling the Sun, and if the Sun was one star among billions in the Milky Way, then perhaps other stars hosted other worlds, other systems, other possibilities for existence itself. The questions that ignited in ancient darkness weren't just about celestial mechanics, they were about our place in a cosmos whose scale and complexity exceeded every human assumption. Those 5 wandering lights in the Babylonian sky were the first hints that the universe contains wonders beyond imagination, operating according to laws that unite the smallest pebble with the most distant star. Standing on that ziggurat 4,000 years ago, surrounded by darkness that modern city dwellers never experience, that anonymous astronomer couldn't know she was taking humanity's first steps toward understanding our cosmic address. The questions she asked while watching those wandering stars would eventually lead us to discover that we live in a universe containing 2,000 billion galaxies, each with hundreds of billions of stars, many hosting planets of their own. The darkness that embraced her wasn't empty. It was pregnant with mysteries that would captivate our own species for millennia to come. Number. In 1823, Heinrich Olbers stood at his observatory window in Bremen, Germany, contemplating what should have been impossible. The German physician and amateur astronomer had spent decades mapping stars, discovering comets, and calculating asteroid orbits. But on this particular night, it wasn't what he could see that captivated him, it was what he couldn't. The darkness between stars held a paradox that would shatter humanity's understanding of existence itself. Olbers realized that if the universe were truly infinite and eternal, filled with stars scattered throughout endless space, then no matter which direction you looked, your line of sight would eventually hit a star's surface. Imagine standing in an infinite forest where every tree extends infinitely upward. No matter where you turn your gaze, you'd see nothing but tree trunks stretching to infinity. Similarly, an infinite universe packed with stars should present a sky that blazes with the brightness of 10,000 suns. Yet when Olbers looked up, darkness dominated. Here's what's really happening. That simple observation, the fact that night exists at all, was humanity's first clue that the universe has a history, a beginning, perhaps even an end. The darkness wasn't empty space. It was time made visible. But Olbers couldn't know this yet. Neither could the brilliant minds who had pondered this puzzle before him. Edmund Halley, famous for the comet that bears his name, had wrestled with the same question decades earlier. If space contained infinite stars, he reasoned, their combined light should make the night sky infinitely bright. Jean-Philippe Loys de Chezeaux, a Swiss astronomer, had calculated that even if stars were distributed in shells around Earth, their cumulative brightness should illuminate the night like day. The paradox seemed to have no solution within the accepted cosmic framework. Most astronomers simply ignored it, focusing on problems they could solve with the tools at hand. After all, the night sky was demonstrably dark. Whatever caused this darkness lay beyond their ability to understand or measure. Then Edgar Allan Poe entered the conversation. Yes, the same Edgar Allan Poe who wrote The Raven and The Telltale Heart proposed in 1848 what would prove to be one of the most profound insights in cosmology. In his prose poem, Eureka, Poe suggested that darkness existed because the universe had a beginning. Light from the most distant stars simply hadn't had enough time to reach Earth yet. Were the succession of stars endless, Poe wrote, then the background of the sky would present us a uniform luminosity, like that displayed by the galaxy, since there could be absolutely no point in all that background at which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions, would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. Poe's poetic intuition cut straight to the heart of cosmic reality. The horror writer had reasoned his way to a universe with a beginning billions of years before Edwin Hubble would prove it through observation. But Poe's contemporaries, trained in rigorous mathematical astronomy, dismissed the insights of a mere poet. They couldn't know that imagination sometimes reaches truth faster than calculation. Lord Kelvin, one of the 19th century's greatest physicists, approached the problem with characteristic mathematical precision. If Poe was right about cosmic darkness implying cosmic youth, then how old could the universe actually be? Kelvin calculated that for the night sky to remain dark, the universe must be younger than 100 trillion years, a number that seemed impossibly vast, yet would prove far too generous. The darkness between stars had become humanity's cosmic clock, ticking away the eons since creation, but reading that clock required understanding what made it tick. The breakthrough came in 1929 when Edwin Hubble, working at the Mount Wilson Observatory in California, discovered that the universe itself was expanding. Using the new 100-inch Hooker telescope, then the world's largest Hubble, measured the distances to nearby galaxies by identifying Cepheid variable stars within them. These remarkable stars pulse with clockwork regularity, and their pulsation period reveals their intrinsic brightness. By comparing their true brightness to how bright they appeared from Earth, Hubble could calculate their distances with unprecedented accuracy. What he found revolutionized our understanding of cosmic scale. The so-called spiral nebulae weren't nearby gas clouds within our Milky Way galaxy. They were entire galaxies, millions of light-years away. But Hubble's distance measurements revealed something even more startling. Every galaxy he studied was racing away from us, and the farther away a galaxy lay, the faster it receded. The universe wasn't static. It was expanding like a balloon being inflated, carrying galaxies away from each other as space itself stretched. Here's what this means for cosmic darkness. As the universe expands, it pulls starlight across vast distances, stretching the light waves like infinite black silk. Light that began its journey as brilliant blue or white radiation arrives at Earth, shifted toward red, infrared, or even radio wavelengths. The most distant galaxies we can detect shine primarily in infrared light, their visible photons stretched beyond our eyes' ability to perceive them. The universe's expansion doesn't just redshift distant light, it dilutes it. Imagine a flashlight beam spreading as it travels. The same amount of light gets distributed over an increasingly large area, making it fainter with distance. Now, add the expansion of space itself, which further dims distant sources. The combination ensures that light from the most remote galaxies contributes almost nothing to the night sky's brightness, even if countless billions of such galaxies exist. Hubble's discovery also provided the universe with an age. If galaxies are flying apart today, then in the past they must have been closer together. Running the cosmic movie backward, there must have been a moment when everything we can observe was compressed into an infinitesimally small point. The universe had a beginning, what astronomer Fred Hoyle would mockingly call the Big Bang during a BBC radio broadcast in 1949, not knowing his sarcastic term would stick forever. The Big Bang theory explained Olber's paradox with elegant simplicity. The night sky is dark because the universe is young, only 13.8 billion years old. Light from the most distant galaxies has been travelling toward us since the universe was a fraction of its current age, but space has been expanding during that entire journey, stretching and dimming the light until it contributes virtually nothing to nighttime brightness. But the story of cosmic darkness was far from complete. In 1965, two researchers at Bell Labs in New Jersey made a discovery that would confirm the Big Bang theory and provide direct evidence for the universe's fiery birth. Arno Penzias and Robert Wilson were trying to eliminate interference from their sensitive radio antenna when they detected a persistent background hiss coming from all directions in space. No matter where they pointed their instrument, no matter what time of day or night they observed, the signal remained constant. They cleaned bird droppings from their antenna, checked their electronics, and eliminated every possible source of contamination. The hiss persisted. What they had found was the cosmic microwave background, the cooled afterglow of creation itself. In the first 380,000 years after the Big Bang, the universe was hot enough and dense enough to be opaque, like the interior of a star. Photons couldn't travel far before being absorbed and re-emitted by free electrons, but as the universe expanded and cooled, protons and electrons combined to form hydrogen atoms for the first time. Suddenly, space became transparent, and light could travel freely across cosmic distances. That first light, released when the universe was only 380,000 years old, has been traveling through space ever since, stretched by cosmic expansion from visible wavelengths to microwaves. Today, it fills the entire universe with radiation at a temperature of 2.7 degrees above absolute zero, barely above the coldest temperature possible in nature. The cosmic microwave background is the most perfect blackbody radiation ever measured, matching theoretical predictions to within 1 part in 100,000. Its discovery earned Penzias and Wilson the Nobel Prize and provided the smoking gun evidence for the Big Bang theory. We live in a universe filled with the stretched and cooled light from its own birth. Here's what this means for the darkness that Olbers pondered. The night sky isn't truly dark at all. It's filled with ancient light from the universe's infancy, but that light has been stretched to wavelengths our eyes can't see. If we could see microwaves, the night sky would glow with a faint, uniform luminosity, the ghost of creation, still haunting space after nearly 14 billion years. The cosmic microwave background also revealed the universe's baby picture. Tiny temperature variations in this ancient radiation, differences of mere millionths of a degree, mapped the density fluctuations in the primordial universe. These variations were the seeds from which galaxies, stars, and planets would eventually grow. The Planck satellite, launched in 2009, mapped these fluctuations with exquisite precision, creating a detailed portrait of the universe when it was only 380,000 years old. But cosmic darkness held more secrets. In 1998, two teams of astronomers studying distant supernovas, exploding stars that can briefly outshine entire galaxies, made a discovery that defied every expectation. They were measuring how fast the universe's expansion was slowing down due to gravity's pull on all the matter it contained. What they found instead was that the expansion was speeding up. Some invisible force was pushing space apart faster and faster, overwhelming gravity's attractive pull. Astronomers named this mysterious influence dark energy, and it comprises 68% of the universe, more than matter and radiation combined. Dark energy makes cosmic darkness even darker, accelerating the expansion that stretches and dims light from distant sources. The discovery of dark energy revealed that we live in a universe where 95% of everything remains invisible and mysterious. Dark matter, detected through its gravitational effects on visible matter, accounts for another 27%. Everything we can see, every star, planet, gas cloud, and grain of dust represents less than 5% of cosmic reality. This realization transformed Olber's paradox into a profound meditation on the nature of existence itself. The darkness between stars isn't just the absence of light, it's the signature of invisible forces and unknown substances that dominate the cosmos. When ancient astronomers looked up at the night sky, they were staring into a universe where most of reality hides beyond their senses, detectable only through its influence on the small fraction they could observe. Modern space telescopes have pushed deeper into cosmic darkness than Olber's could have imagined possible. The Hubble Space Telescope's deep-field observations stared at seemingly empty patches of sky for days at a time, collecting every photon that arrived from the most distant galaxies. What appeared dark to ground-based telescopes revealed thousands of galaxies stretching back to when the universe was less than 1 billion years old. The recently launched James Webb Space Telescope peers even further into the cosmic past, using infrared detectors to capture light that has been stretched beyond visible wavelengths by cosmic expansion. It sees galaxies that formed when the universe was only a few 100 million years old, during what astronomers call the cosmic dawn, the era when the first stars ignited and began burning away the hydrogen fog that filled space. Each deeper look into darkness reveals new mysteries. Webb has found galaxies that are too massive and mature for their cosmic age, challenging our understanding of how quickly structures can form in the early universe. It has detected water vapor in the atmospheres of exoplanets, organic molecules in stellar nurseries, and complex chemistry in the most distant galaxies we've ever observed. The darkness that Olbers contemplated from his window in Bremen has become humanity's gateway to cosmic history. Every dark patch of sky contains galaxies we haven't yet seen, stars that died before Earth was born, and light that has been traveling toward us since the universe was young. The night sky is dark not because space is empty, but because we exist in a universe with a finite age and an infinite capacity to surprise us. Standing under stars tonight, we see the same darkness that puzzled Heinrich Olbers 2 centuries ago. But now we understand that this darkness tells the story of cosmic time itself, a universe that began in fire, expanded through eons of creation, and continues to evolve in ways that push the boundaries of human comprehension. The dark canvas of night sky isn't empty space waiting to be filled. It's time made visible, carrying messages from the deepest past and hints of an uncertain future. For 4 centuries after Galileo first glimpsed Jupiter's 4 largest moons dancing around their giant host, astronomers believed planets were precious accidents in a cosmos of lonely stars. Our solar system, with its orderly procession of worlds from scorching Mercury to distant Neptune, seemed like a cosmic fluke, a rare arrangement of matter that might exist nowhere else in the universe. Then October 6, 1995, changed everything. Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in southeastern France, announced the discovery of a world that shattered every assumption about how planets form and behave. Orbiting the sun-like star 51 Pegasi, 48 light-years from Earth, they had found a planet that shouldn't exist. This world, later named 51, Pegasi b, was a gas giant bigger than Jupiter, but orbiting its star in just 4.2 days. It raced around 51 Pegasi at a distance of only 4.6 million miles, 8 times closer than Mercury orbits our Sunday. The planet's atmosphere boiled at 2,000 degrees Fahrenheit, hot enough to melt copper. Everything astronomers thought they knew about planetary systems had just been turned upside down. Here's what's really happening. Meyer and Queloz couldn't see the planet directly. It was far too small and dim to detect next to its blazing star. Instead, they measured the subtle wobble that the planet's gravity induced in its host star's motion. As the unseen world orbited, its gravitational pull tugged the star first toward us, then away, creating tiny shifts in the star's light that revealed the hidden companion's presence. The technique, called the radial velocity method, requires extraordinary precision. 51 Pegasi b causes its star to wobble at a leisurely 59 meters per second, about the speed of a running human. Detecting this motion from 48 light-years away is like measuring a person's walking pace from the distance of Saturn. Yet Meyer and Queloz's spectrograph could detect velocity changes of just a few meters per second, sensitive enough to catch a star's gravitational dance with worlds much smaller than Jupiter. The discovery opened floodgates that are still pouring forth new worlds today. Within months, other teams found additional hot Jupiters, massive planets, skimming the surfaces of their stars in orbits that lasted mere days. These worlds defied every model of planetary formation. Jupiter-sized planets were supposed to form far from their stars, where water could freeze into ice and provide the solid foundation needed to build massive cores. Yet here were gas giants orbiting closer to their stars than Mercury orbits the Sunday. The explanation revolutionized planetary science. These giants formed in the cold outer regions of their stellar systems, then migrated inward through gravitational interactions with the disk of gas and dust that surrounded their young stars. Some spiraled all the way to their stars' surfaces, while others stopped at various distances, creating the hot Jupiter population we observe today. But hot Jupiters were just the beginning. As detection methods improved and observing programs expanded, astronomers found planets that stretched imagination to its breaking point. They discovered worlds orbiting backward retrograde planets, whose orbits run opposite to their star's rotation. They found planets with days shorter than Earth hours, and others with years lasting mere weeks. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet discovery by staring continuously at 150,000 stars simultaneously. Instead of measuring stellar wobbles, Kepler watched for transits, the telltale dimming when planets crossed their stars' faces as seen from Earth. The technique revealed planets too small to detect through radial velocity measurements, opening the door to discovering Earth-sized worlds. Kepler's harvest exceeded all expectations. In its original 4-year mission, later extended through the K2 program, the telescope found over 2,700 confirmed planets and identified thousands more candidates awaiting verification. Each discovery rewrote the rules of what planets could be and where they could exist. Consider Kepler 7b, where the daytime side reaches 4,000 degrees Fahrenheit, while the nighttime side approaches -200 degrees, a temperature difference greater than between molten lava and frozen nitrogen. This tidally locked world always shows the same face to its star, creating permanent day and night hemispheres with winds that could reach 7,000 miles per hour, trying to transport heat from the scorching day side to the frozen night side. Or examine HD 189733b, where the upper atmosphere contains tiny particles of aluminum oxide and titanium oxide, the same compounds found in rubies and sapphires. On this world, gemstones literally rain from the sky, condensing in the cooler upper atmosphere and falling as precious precipitation toward the surface below. The variety defied every attempt at categorization. Astronomers found planets made of diamond crystallized carbon worlds formed from the compressed remains of carbon-rich stars. They discovered worlds where glass rained sideways in 7,000-mile-per-hour winds, and planets where the surface pressure could crush a human body in microseconds. WASP-12b represents one of the most dramatic examples of planetary destruction ever observed. This unfortunate world orbits so close to its star that stellar gravity is literally tearing it apart, stripping away 6 billion metric tons of planetary material every second. The planet is spiraling inexorably inward toward its fiery doom, expected to be completely devoured within 10 million years, a cosmic eye blink. Yet perhaps the most remarkable discovery was Kepler-16b, a world that watches 2 sunsets every day. This planet orbits both stars of a binary system, following a circumbinary orbit that takes it around both stellar companions. Standing on its surface, if it had a solid surface to stand on, you would see 2 suns of different colors chasing each other across an alien sky. Science fiction became science fact when astronomers found real-world Tatooines scattered throughout the galaxy. Even more exotic are the planets orbiting PSRB 1257 plus 12, a pulsar, 37,000 light-years away. Pulsars are the collapsed cores of massive stars that have exploded as supernovas, leaving behind objects so dense that a teaspoon of their material would weigh as much as Mount Everest. This particular pulsar spins 701 times per second, sweeping beams of radiation across space like a cosmic lighthouse. 3 planets orbit this stellar corpse, somehow surviving the supernova explosion that created their unusual Sunday. These worlds are bathed in radiation levels that would sterilize any known form of life in moments, yet they maintain stable orbits around an object that packs more mass than our Sun into a sphere only 12 miles across. The planets were likely formed from the debris of the supernova explosion itself, born from stellar death in one of the universe's most violent processes. The Spitzer Space Telescope added infrared eyes to humanity's planet-hunting toolkit, detecting the heat signatures of distant worlds and mapping temperature variations across their surfaces. Spitzer measured the day-night temperature differences on dozens of exoplanets, revealing which worlds have thick atmospheres that distribute heat efficiently and which are tidally locked with permanent hot and cold sides. One of Spitzer's most significant contributions was detecting water vapor in exoplanet atmospheres. HD 209458b, a gas giant slightly smaller than Jupiter, became the first exoplanet with confirmed atmospheric water when Spitzer detected the characteristic infrared absorption signatures of water molecules in the planet's spectrum. This discovery opened the field of exoplanet atmospheric characterization, allowing astronomers to analyze the chemical composition of worlds orbiting other stars. The transit technique also revealed planets with the most extreme orbital configurations imaginable. HATP 7b orbits its star in just 2.2 days, while also orbiting backward retrograde motion that suggests a violent dynamical history involving gravitational interactions that flipped the planet's orbit completely around. Some planets have orbits so elliptical that they experience 1,000-degree temperature swings as they swing from their closest to farthest approach to their stars. Multi-planet systems proved even more diverse than single planets. The TRAPPIST-1 system contains 7 Earth-sized planets orbiting an ultra-cool dwarf star just 40 light-years away. All 7 worlds are tidally locked and packed so tightly together that from the surface of one planet, the others would appear larger in the sky than our moon appears from Earth. 3 of these worlds orbit in their star's habitable zone, where liquid water could theoretically exist on their surfaces. The Kepler-90 system challenges our understanding of how tightly planets can be packed together. This system contains at least 8 confirmed planets, orbiting closer to their star than Earth orbits the Sunday. The planets are arranged in a complex chain of orbital resonances, where their orbital periods are related by simple ratios that prevent them from colliding, despite their crowded configuration. Ground-based surveys have discovered planets around the most unlikely stars. Captain's star, one of the oldest stars in the galaxy at 11.5 billion years old, hosts at least one potentially habitable planet. This ancient world formed when the universe was less than 25% of its current age, raising profound questions about how early in cosmic history planets and possibly life could emerge. The most abundant type of planet in the galaxy appears to be one that doesn't exist in our solar system, super-Earths. These worlds are larger than Earth but smaller than Neptune, with masses ranging from twice Earth's mass up to 10 times our planet's bulk. Kepler found that super-Earths are extraordinarily common, orbiting roughly 40% of Sun-like stars, yet our solar system completely lacks such worlds, making us the exception rather than the rule. Some super-Earths orbit in their stars' habitable zones, where temperatures allow liquid water to exist on planetary surfaces. Kepler 452b, located 1,400 light-years away, is only 60% larger than Earth, and receives almost exactly the same amount of energy from its star that Earth receives from the Sunday. This world might harbour oceans, continents, and perhaps even life, though we have no way to determine its surface conditions with current technology. The James Webb Space Telescope has begun analysing exoplanet atmospheres with unprecedented precision, detecting water vapour, carbon dioxide, and even clouds in the atmospheres of distant worlds. Webb's first exoplanet spectrum analysed WASP-96b, revealing water signatures that were 5 times more precise than any previous measurement. The telescope can detect atmospheric components that reveal whether planets formed close to their current orbits or migrated from elsewhere in their systems. Perhaps most tantalizingly, astronomers have identified potentially habitable worlds orbiting within the habitable zones of nearby stars. Proxima Centauri b, just 4.2 light-years away around our closest stellar neighbour, receives about 70% of the energy that Earth receives from the Sunday. Gliese 667 cc, 11.1 light-years distant, might be temperate enough to support liquid water despite orbiting a red dwarf star. Today we know of over 5,000 confirmed exoplanets, with thousands more candidates awaiting verification. Every week brings announcements of new discoveries, each adding another piece to the puzzle of planetary formation and evolution. The Transiting Exoplanet Survey Satellite, or TESS, continues Kepler's legacy by surveying the entire sky for planets orbiting the brightest nearby stars. The numbers suggest we live in a universe where planets vastly outnumber stars. Conservative estimates indicate our galaxy contains at least 100 billion planets, with perhaps 40 billion orbiting in their stars' habitable zones where liquid water could exist. The Milky Way alone might harbour more potentially habitable worlds than there are people on Earth. Yet for all the thousands of planets we've discovered, we still haven't found Earth's twin, a world with our planet's size, mass, and orbital distance around a sun-like star. We've found planets larger than Earth orbiting in habitable zones, and Earth-sized planets orbiting closer to their stars. But the combination that created our temperate, life-bearing world remains elusive in our current surveys. This absence might be an observational bias. Earth-sized planets in Earth-like orbits around Sun-like stars are among the most difficult to detect with current methods. They cause tiny stellar wobbles and create brief, shallow transits that challenge the limits of our instruments. The next generation of telescopes and detection methods will probe deeper into this parameter space, potentially revealing whether Earth-like worlds are common or rare. The search for exoplanets has transformed from asking whether other worlds exist to cataloguing their incredible diversity and attempting to understand the physical processes that create such variety. Every new discovery expands our conception of what a planet can be, from diamond worlds and lava planets to ice giants and super-Earths with no solar system analogues. Standing under tonight's stars, we can look up knowing that almost every point of light harbours worlds of its own. The night sky has transformed from a scattering of lonely lights to an infinite garden where every star tends planets we're only beginning to imagine. Some of these worlds might harbor life, perhaps even intelligence that gazes back across the cosmic distances, wondering, like us, whether they're alone. The ancient questions that first stirred human curiosity about the wandering stars have evolved into a comprehensive survey of planetary systems throughout our galactic neighborhood. We've learned that our solar system is just one example of nature's creativity, neither typical nor unique, but part of a vast cosmic ecosystem of worlds that stretches as far as telescopes can see and likely beyond. William Herschel made his revolutionary discovery by accident on February 11th, 1800, while conducting what seemed like a routine experiment in his observatory in Bath, England. The astronomer who had discovered Uranus 20 years earlier was now investigating whether different colors of sunlight carried different amounts of heat. He split sunlight through a prism, creating a rainbow spectrum, then placed thermometers at various positions to measure each color's temperature. Blue light registered cool. Green was warmer, orange warmer still, red was hottest of all. But when Herschel moved his thermometer just beyond the red edge of the visible spectrum into what appeared to be empty space, his instrument recorded the highest temperature yet. The universe had been speaking in a language human eyes couldn't read, and we'd been deaf to most of the conversation. Here's what's really happening. Herschel had discovered infrared radiation heat rays that exist beyond the red limit of human vision. Light, he realized, was in flight, far more than what our eyes could detect. The electromagnetic spectrum stretched beyond visible wavelengths in both directions, carrying information about cosmic phenomena that remained invisible to every astronomer who had ever lived. This revelation transformed astronomy from a purely visual science into something far more comprehensive. If stars and planets emitted invisible light, then the universe contained whole categories of objects and processes that telescopes had never glimpsed. Cosmic events might be occurring all around us, broadcasting their signatures in wavelengths our eyes simply couldn't perceive. The implications staggered the imagination. For thousands of years, astronomers had been like people trying to understand a symphony while listening to only one instrument. The cosmic orchestra was playing in frequencies spanning dozens of octaves, but human senses could perceive only the narrow range we call visible light, roughly 1 octave out of the electromagnetic spectrum's vast range. Johann Ritter quickly discovered the spectrum's other extreme. In 1801, just 1 year after Herschel's breakthrough, the German physicist placed silver chloride, a chemical that darkens when exposed to light beyond the violet edge of the visible spectrum. The chemical reacted even more strongly than it did to visible violet light, revealing ultraviolet radiation streaming from the sunday. The electromagnetic spectrum, as scientists would eventually understand it, spans from radio waves with wavelengths measured in kilometers to gamma rays with wavelengths smaller than atomic nuclei. Visible light occupies a tiny slice of this vast range, roughly 400 to 700 nanometers. Everything else remained hidden from human perception, carrying information about the universe that no one had ever imagined. For over a century, these discoveries remained scientific curiosities with little astronomical application. Building detectors sensitive to invisible wavelengths required technologies that wouldn't be invented for generations. Astronomers continued mapping the visible universe, while electromagnetic messages from cosmic phenomena streamed past Earth, undetected and unread. Then, in 1932, Carl Jansky changed everything. Working at Bell Labs in New Jersey, Jansky was investigating radio interference that affected transatlantic telephone communications. He built a rotating antenna system. Locals called it Jansky's merry-go-round to track down the source of persistent radio static. The young engineer identified 2 sources quickly: nearby thunderstorms and distant lightning strikes. But a third source of radio noise puzzled him completely. This mysterious signal appeared strongest when certain star patterns were highest in the sky. After months of careful observation, Jansky realized the radio emissions were coming from the center of the Milky Way galaxy, 26,000 light-years away. He had accidentally opened an entirely new window on the universe radio astronomy. The discovery launched a revolution that continues today. Radio waves penetrate dust clouds that completely block visible light, allowing astronomers to peer into stellar nurseries where baby stars gestate for millions of years. Radio telescopes revealed the galaxy's spiral structure by mapping hydrogen gas that emits characteristic 21-centimeter radiation. They discovered pulsars spinning neutron stars that sweep beams of radio waves across space like cosmic lighthouses. Radio astronomy's early discoveries defied every expectation. In 1963, astronomers identified radio sources so powerful they outshone entire galaxies while appearing as mere points of light in optical telescopes. These quasars' quasi-stellar radio sources are now understood to be supermassive black holes actively feeding on surrounding matter. The accretion process releases more energy than 10 trillion suns, making quasars visible across billions of light-years. Some radio sources exhibited even stranger behavior. In 1967, Jocelyn Bell Burnell and Anthony Hewish discovered radio signals pulsing with clockwork precision every 1.3 seconds. The signals were so regular that researchers initially wondered whether they had detected artificial transmissions from an alien civilization. They even nicknamed the source LGM-1 for Little Green Men. The truth proved far more exotic than alien technology. These pulsars were neutron stars, the collapsed cores of massive stars that had exploded as supernovas. Each pulsar packed more mass than our Sun into a sphere only 12 miles across, spinning hundreds of times per second while sweeping beams of radio emission across the galaxy. The fastest pulsar rotates 716 times per second, its surface moving at nearly 20% of light speed. Meanwhile, infrared astronomy began revealing hidden aspects of familiar objects. Cool stars too dim to detect invisible light blazed brightly when observed at infrared wavelengths. Brown dwarfs failed stars too small to sustain. Nuclear fusion became visible as infrared sources radiating their leftover heat from formation. Planets around other stars, completely lost in their host star's visible glare, showed up clearly in infrared images. The Spitzer Space Telescope, launched in 2003, demonstrated infrared astronomy's transformative power. Operating beyond Earth's atmosphere to avoid interference from atmospheric water vapor, Spitzer could detect infrared radiation from objects billions of light-years away. The telescope peered through cosmic dust to find star formation regions hidden from optical telescopes, revealing that the universe creates new stars at a much higher rate than visible light observations had suggested. Spitzer discovered that nearly every galaxy contains a supermassive black hole at its center, surrounded by a torus of hot dust that radiates intensely in infrared wavelengths. These active galactic nuclei can outshine all their galaxy's stars combined, but their signatures are often hidden by dust that absorbs visible and ultraviolet light while re-radiating the energy at infrared wavelengths. X-ray astronomy opened perhaps the most violent chapter in the electromagnetic spectrum story. X-rays are produced by matter heated to millions of degrees temperatures that exist only in the most extreme cosmic environments. The first cosmic X-ray source, discovered by rocket-borne detectors in 1962, turned out to be Scorpius Zone, a neutron star pulling matter from a companion star and heating it to tens of millions of degrees in the process. The Chandra X-ray Observatory, launched in 1999, revealed a universe where violence operates on scales that dwarf human comprehension. Chandra images show supernova remnants expanding shock waves from exploded stars that heat surrounding gas to 50 million degrees Fahrenheit. The observatory detected X-ray emissions from matter falling into black holes, revealing how these cosmic monsters heat in falling material to temperatures where atomic nuclei move at significant fractions of light speed. Perhaps most remarkably, Chandra discovered that galaxy clusters, the largest gravitationally bound structures in the universe, are filled with hot gas at temperatures exceeding 100 million degrees. This intergalactic medium contains more normal matter than all the galaxies in the cluster combined, but remained invisible until X-ray telescopes could detect its thermal emissions. Gamma-ray astronomy opened the electromagnetic spectrum's most energetic frontier. Gamma rays are produced by the universe's most violent processes: matter-antimatter, annihilation, radioactive decay of exotic particles, and electrons accelerated to nearly light speed in magnetic fields stronger than any produced Fock. On Earth, the first gamma-ray sources discovered were gamma-ray bursts, brief flashes of the most energetic electromagnetic radiation in the universe. These bursts can release more energy in 10 seconds than our Sun will produce in its entire 10 billion-year lifetime. For decades, astronomers couldn't determine what caused these cosmic explosions because gamma-ray detectors couldn't pinpoint their locations precisely enough to identify counterparts at other wavelengths. The mystery was solved when the Swift satellite began detecting gamma-ray bursts and immediately alerting ground-based telescopes to observe their locations. These observations revealed that gamma-ray bursts are produced by two types of cosmic catastrophes: the collapse of extremely massive stars into black holes, and the collision of neutron stars or neutron-star black hole pairs. The Fermi Gamma-ray Space Telescope revealed that our galaxy's center hosts a supermassive black hole that occasionally flares with gamma-ray emissions as it consumes nearby matter. Even more surprising, Fermi detected gamma-ray emissions from thunderstorms on Earth. Terrestrial gamma-ray flashes produced when lightning creates brief antimatter reactions in our planet's upper atmosphere. Ultraviolet astronomy completed the electromagnetic spectrum's high-energy end, revealing phenomena invisible to ground-based telescopes. Earth's atmosphere absorbs most ultraviolet radiation, protecting life from harmful UV rays but also blocking astronomical observations. Space-based UV telescopes like the Hubble Space Telescope's UV instruments revealed that many stars emit most of their energy at ultraviolet wavelengths. Hot, young stars pour out intense UV radiation that ionizes hydrogen gas in nearby nebulae, creating the glowing emission regions that appear as red clouds in visible light images. The hottest stars, Wolf-Rayet stars with surface temperatures exceeding 100,000 degrees, are virtually invisible to 5 optical telescopes but blaze like beacons in ultraviolet light. UV observations also revealed the cosmic web's large-scale structure by detecting absorption lines from hydrogen gas between galaxies. This intergalactic medium, heated and ionized by UV radiation from quasars and star-forming galaxies, creates absorption signatures in the spectra of distant objects. Mapping these absorption systems revealed that normal matter is distributed in vast filaments connecting galaxy clusters, the cosmic web that forms the universe's largest-scale architecture. Each wavelength band tells its own story about cosmic evolution. Radio telescopes map the cold hydrogen gas from which new stars form. Infrared detectors peer through dust to watch star birth in action. Visible light reveals mature stellar populations and galaxy structures. Ultraviolet radiation traces hot, young stars and energetic processes. X-rays expose matter heated to extreme temperatures around compact objects. Gamma rays mark the universe's most violent events. The synergy between different wavelengths has revolutionized our understanding of cosmic phenomena. Consider a supernova explosion observed across the electromagnetic spectrum. Gamma rays and X-rays reveal the initial shockwave breakthrough. Ultraviolet and optical light trace the expanding fireball. Infrared radiation maps dust condensing in the cooling ejector. Radio waves track the shockwave's interaction with surrounding gas for decades after the explosion. Multi-wavelength astronomy has revealed that many cosmic objects are fundamentally different from their visible light appearance suggests. Active galactic nuclei that appear as unremarkable points of light in optical telescopes blaze with the power of billions of suns when observed at radio, infrared, X-ray, and gamma-ray wavelengths. Star-forming regions hidden behind opaque dust clouds in visible light reveal themselves as bustling stellar nurseries in infrared observations. The electromagnetic spectrum also serves as a cosmic time machine. Different wavelengths probe different epochs in universal history. The cosmic microwave background stretched to millimeter wavelengths by cosmic expansion reveals the universe when it was only 380,000 years old. Far infrared observations detect galaxies from when the universe was less than 1 billion years old, during the epoch when the first generation of stars was rapidly forming. Visible and near-infrared telescopes observe mature galaxies from the universe's middle age. Radio telescopes detect hydrogen gas that will fuel star formation for billions of years to come. Modern telescopes are designed as multi-wavelength observatories that can observe the same cosmic phenomena simultaneously across different parts of the electromagnetic spectrum. The James Webb Space Telescope operates primarily in near-infrared wavelengths, but can observe from 600 nanometers to 28 micrometers, nearly spanning from visible red light to mid-infrared radiation. This broad spectral coverage allows Webb to track how galaxy properties change with wavelength, revealing information about stellar populations, gas content, and dust distribution that no single wavelength telescope could provide. The Atacama Large Millimeter, divided by submillimeter array, ALMA, observes at the boundary between infrared and radio wavelengths, detecting radiation from molecules in space. ALMA can observe carbon monoxide, water vapor, ammonia, and dozens of other molecular species in star-forming regions, planetary nebulae, and even in the atmospheres of planets in our solar system. These molecular observations reveal the chemical complexity of space, showing that even the emptiest regions between stars contain a rich inventory of organic compounds. Future observatories will push multi-wavelength astronomy even further. The proposed Origin Space Telescope would observe in far infrared wavelengths that are completely blocked by Earth's atmosphere, detecting the peak thermal emission from objects at temperatures from 30 to 300 degrees above absolute zero. This coverage would reveal planet formation in progress around nearby stars and trace the cosmic history of water throughout the universe. Gravitational wave astronomy, though not electromagnetic in nature, has joined the multi-messenger approach to cosmic observation. When the Laser Interferometer Gravitational Wave Observatory detected merging black holes in 2015, it opened an entirely new sensory channel for exploring the universe. Gravitational waves carry information that electromagnetic radiation cannot provide, revealing the dynamics of space-time itself during the universe's most extreme events. The combination of gravitational waves with electromagnetic observations has already produced groundbreaking discoveries. In 2017, LIGO and Virgo detected gravitational waves from merging neutron stars, while electromagnetic telescopes across the world observed the event's light across all wavelengths. This multi-messenger observation revealed that neutron star mergers are the primary source of gold, platinum, and other heavy elements in the universe, forging these precious metals in conditions so extreme they can only exist during cosmic collisions. Here's what this means for our understanding of the universe. Every wavelength of light carries unique information about cosmic processes, and only by combining observations across the entire electromagnetic spectrum can we understand how the universe truly works. The cosmos is not just brighter than we imagined, it's speaking to us in dozens of electromagnetic languages simultaneously, each carrying messages about different aspects of cosmic evolution. Standing under tonight's stars, we can appreciate that our eyes capture only the tiniest fraction of the information streaming toward Earth from across the a universe. Radio waves from distant galaxies are passing through your body right now, carrying news of star formation and black hole activity from billions of light years away. Infrared radiation from nearby star-forming regions warms your skin by invisible amounts. Cosmic gamma rays, heavily attenuated by Earth's atmosphere, still occasionally strike the upper layers of our air, carrying signatures of the universe's most violent processes. The night sky that ancient astronomers observed was just the opening movement in a cosmic symphony playing across dozens of octaves. Modern astronomy has given us instruments to hear the full orchestra, revealing a universe far more dynamic, interconnected, and spectacular than human eyes alone could ever perceive. The electromagnetic spectrum has transformed the static heavens of antiquity into a cosmos alive with energy, motion, and messages traveling at the speed of light from the edge of observable space. Each new detector, each unexplored wavelength, each technological advance reveals new aspects of cosmic reality. The universe continues to surprise us because we're still learning its languages, still developing the sensitivity to hear whispers from the most distant galaxies and the most exotic objects. The hidden tongues that William Herschel first detected in 1800 have become humanity's Rosetta Stone for translating cosmic phenomena into human understanding. In 1933, Fritz Zwicky made a discovery that would haunt astronomy for nearly a century. The Swiss-American astronomer was weighing the Coma Galaxy Cluster, a collection of over 1,000 galaxies bound together by their mutual gravitational attraction, when he realized something was terribly wrong with the Sol universe. Zwicky measured how fast individual galaxies moved within the cluster, using the Doppler shift of their light to calculate their velocities. Some galaxies raced toward Earth while others fled away, but their average motion revealed how quickly they orbited around the cluster's gravitational center. The faster they moved, the more massive the cluster had to be to keep them gravitationally bound. When Zwicky added up all the mass, he could see every star in every galaxy, all the gas glowing between them, every grain of dust. The total fell dramatically short of what the galaxy motions demanded. The visible matter could account for only about 10% of the gravitational mass required to hold the cluster together. Galaxies whirled around each other so fast they should have flung apart billions of years ago, scattering across the cosmos like debris from a cosmic explosion. Yet there they were, serenely orbiting in gravitational harmony. Something invisible held them together, something that outweighed all the stars, gas, and dust combined by a factor of 9 to 1. Here's what's really happening. Zwicky had discovered the universe's greatest mystery. Most of the matter in the cosmos doesn't emit, absorb, or reflect light. It ignores electromagnetic forces entirely, interacting with normal matter only through gravity's inexorable pull. This invisible substance, which Zwicky called dark matter, comprises over 85% of all matter in the universe. Yet, we can detect it only through its gravitational effects on the small fraction of matter we can actually see. For decades, most astronomers dismissed Zwicky's calculation as the result of incomplete observations or measurement errors. Surely the missing mass would turn up when telescopes became more sensitive and surveys more complete. Dark matter seemed too strange, too convenient an explanation for observations that didn't match expectations. Then, in the 1970s, Vera Rubin began a systematic study of how galaxies rotate, and everything Zwicky had claimed was vindicated in spectacular fashion. Rubin focused on spiral galaxies similar to our Milky Way, measuring the orbital speeds of stars at various distances from galactic centers. The expectation was straightforward. Stars near a galaxy's center should orbit quickly, held in tight orbits by the gravitational pull of the central bulge. Stars farther out should move more slowly, like planets in our solar system where distant Neptune creeps along its orbit while inner Mercury races around the Sunday. Instead, Rubin found that stars throughout spiral galaxies, from the central regions to the outermost edges, all moved at roughly the same orbital speed. Every galaxy she measured showed this flat rotation curve, indicating that galaxies contained far more mass than their visible components could account for. The implications were staggering. Each spiral galaxy was embedded in an invisible halo of dark matter that extended far beyond the visible stellar disk. These halos contained up to 10 times more mass than all the stars and gas combined. Galaxies weren't just collections of stars held together by their own gravity. They were minor visible components of much larger, invisible structures. Computer simulations of galaxy formation confirmed that dark matter was essential for explaining how cosmic structures evolved. In the early universe, tiny density fluctuations in dark matter grew under their own gravity, eventually becoming massive enough to attract the normal matter that would form stars and galaxies. Without dark matter's gravitational scaffolding, the universe would contain no galaxies, no stars, no planets, and no life. But what is dark matter made of? This question has driven particle physicists and astronomers to extraordinary lengths in their search for answers. Dark matter cannot be made of normal atoms, protons, neutrons, and electrons, because such matter would interact with electromagnetic radiation and be detectable by telescopes. The mysterious substance must consist of exotic particles that experience only gravitational and perhaps weak nuclear forces. The leading candidates are weakly interacting massive particles, WIMPs, hypothetical particles that emerge naturally from theories extending the standard model of particle physics. WIMPs would be stable, electrically neutral, and massive enough to account for dark matter's gravitational effects. They would pass through normal matter like ghosts through walls, occasionally colliding with atomic nuclei in interactions so rare that detecting them requires extraordinary experimental sensitivity. Underground laboratories around the world house detectors designed to catch dark matter particles as they stream through Earth. The Xenon Dark Matter Project, located beneath Italy's Gran Sasso Mountain, uses liquid xenon cooled to -100 degrees Celsius to detect the tiny flashes of light produced when dark matter particles collide with xenon nuclei. The detector is so sensitive it can distinguish between signals from dark matter and background radiation from cosmic rays or natural radioactivity. The Large Underground Xenon Experiment LUX operated 3/4 of a mile underground in South Dakota's former home state gold mine. Surrounded by water tanks to shield against cosmic rays, LUX searched for dark matter interactions over several years of operation. Despite its extraordinary sensitivity, the detector found no convincing evidence for WIMP interactions, placing increasingly stringent limits on dark matter's properties. These null results have forced physicists to consider alternative dark matter candidates. Axion's hypothetical particles, originally proposed to solve problems in quantum chromodynamics, could compose dark matter if they exist in sufficient quantities. Sterile neutrinos, exotic cousins of the nearly massless neutrinos that stream from nuclear reactions, might account for some or all of dark matter's effects. Some researchers have proposed that dark matter consists of primordial black holes formed in the universe's first moments, when density fluctuations collapsed directly into black holes without first forming stars. These primordial black holes could range in mass from asteroids to solar masses, providing dark matter's gravitational effects without requiring exotic particles. Meanwhile, space-based telescopes have mapped dark matter's distribution throughout the universe using gravitational lensing, the way massive objects bend light from background sources. The Hubble Space Telescope has created detailed maps of dark matter in galaxy clusters by analyzing how the cluster's gravity distorts images of distant galaxies seen behind them. These observations reveal that dark matter forms a cosmic web of filaments, connecting galaxy clusters like a three-dimensional spiderweb, spanning billions of light years. Galaxies and galaxy clusters sit at the intersections of this web, where dark matter filaments converge and provide the gravitational wells needed to collect normal matter into stars and planets. The cosmic web's large-scale structure matches predictions from computer simulations of dark matter evolution with remarkable precision. These simulations follow billions of dark matter particles from shortly after the Big Bang to the present day, showing how gravity molds the initial smooth distribution into the web-like patterns we observe today. But dark matter represents only part of the universe's missing components. In 1998, two teams of astronomers studying distant supernovas made a discovery that defied every expectation about cosmic evolution. Type Ia supernovas, exploding white dwarf stars, serve as cosmic standard candles because they all reach nearly the same peak brightness. By comparing their apparent brightness to their known intrinsic luminosity, astronomers can calculate their distances with high precision. The Supernova Cosmology Project and the High-Z Supernova Search Team were using these stellar explosions to measure how fast the universe's expansion was slowing down due to gravity's attractive pull on all the matter it contained. What they found instead overturned cosmology. The universe's expansion was accelerating. Distant supernovas appeared fainter than expected, indicating they were farther away than standard cosmological models predicted. The universe wasn't slowing down, it was speeding up, expanding faster and faster as time progressed. Some invisible force was pushing space apart at an accelerating rate, overwhelming gravity's attempts to slow cosmic expansion. Astronomers named this mysterious influence dark energy, and subsequent observations revealed it comprises approximately 68% of the universe's total energy density. Combined with dark matter's 27% contribution, the invisible components account for 95% of everything that exists. Normal matter atoms, molecules, every star, planet, and living thing represents less than 5% of cosmic reality. Dark energy's nature remains even more mysterious than dark matter's composition. The leading theoretical candidate is vacuum energy, the quantum mechanical energy of empty space itself predicted by particle physics. Even supposedly empty space seethes with virtual particle pairs that briefly appear and annihilate in accordance with Heisenberg's uncertainty principle. This quantum foam should contribute energy density to the universe that could drive accelerating expansion. However, when physicists calculate vacuum energy's expected density using quantum field theory, they get an answer that's larger than observations allow, by a factor of 10 to the 120th power, possibly the worst prediction in the history of science. Either the calculations are fundamentally wrong, or some unknown mechanism cancels vacuum energy's cosmological effects to extraordinary precision. Alternative explanations for dark energy include quintessence, a slowly evolving scalar field that fills space and drives; acceleration. Unlike vacuum energy, which remains constant over time, quintessence could change its properties as the universe evolves, potentially leading to different expansion histories in the cosmic past and future. The Dark Energy Survey, conducted using a powerful camera mounted on a telescope in Chile, has mapped the distribution of galaxies across 1/8 of the entire sky to understand how dark energy affects cosmic structure formation. By measuring how galaxy clustering has evolved over the past several billion years, the survey constrains dark energy's properties and tests whether Einstein's general relativity correctly describes gravity on cosmic scales. The Euclid space mission, launched in 2023, will measure the shapes and distances of 2 billion galaxies to create the most detailed map of dark matter and dark energy ever attempted. By analyzing how dark matter's gravity lenses background galaxies and how dark energy affects the universe's expansion history, Euclid will determine whether dark energy remains constant or evolves over cosmic time. Ground-based experiments complement space missions in probing dark energy's nature. The Dark Energy Spectroscopic Instrument, DESI, measures redshifts for tens of millions of galaxies and quasars, mapping cosmic expansion with unprecedented precision across the universe's recent history. These measurements test whether dark energy's density changes over time, and whether modifications to Einstein's gravity theory might explain accelerating expansion without requiring exotic energy components. The combination of dark matter and dark energy has revolutionized our understanding of cosmic evolution. In the standard lambda CDM model, lambda representing dark energy, CDM standing for cold dark matter, the universe began with quantum fluctuations that seeded structure formation in an expanding spacetime, dominated first by radiation, then by matter, and finally by dark energy. During the radiation-dominated era, the universe was too hot for atoms to form, and dark matter couldn't begin clustering because radiation pressure smoothed out density fluctuations. Once the universe cooled enough for atoms to form about 380,000 years after the Big Bang, dark matter began collapsing into increasingly massive structures, while normal matter followed its gravitational lead. For the first several billion years, matter's gravity slowed cosmic expansion, allowing dark matter halos to grow and merge into increasingly massive structures. Galaxies formed within these halos, fed by cold gas streaming along dark matter filaments. Star formation peaked when the universe was about 3 billion years old, during the epoch when dark matter structures had grown large enough to efficiently collect gas, while dark energy remained too weak to significantly affect structure formation. As the universe continued expanding, dark energy gradually became the dominant component, eventually overwhelming matter's gravity and accelerating cosmic expansion. This transition occurred approximately 5 billion years ago, around the time our solar system formed. Since then, dark energy's repulsive effects have increasingly suppressed structure formation, and the universe has entered an era of exponential expansion that will continue indefinitely. The far future belongs to dark energy. As expansion accelerates, galaxy clusters will be pushed apart until each becomes isolated in its own expanding region of space. Eventually, even the Milky Way and Andromeda, currently approaching each other and destined to merge in approximately 4 billion years, will be separated by dark energy's relentless expansion. The observable universe will shrink as distant galaxies disappear beyond our cosmological horizon, leaving future astronomers with only local galaxy groups to study. Yet we're living during a unique epoch in cosmic history, when both dark matter and dark energy significantly influence the universe's behavior. Dark matter has had enough time to build the cosmic web's large-scale structure, while dark energy hasn't yet completely halted structure formation. We can observe the full range of cosmic phenomena, from the cosmic microwave background, which reflects conditions when the universe was matter-dominated, to distant supernovas that reveal dark energy's effects on recent expansion. History. Here's what this means for our place in the universe. We exist in a cosmos where 95% of everything remains invisible and poorly understood. The matter we're made of, the planets we inhabit, the stars that light our sky, all of it represents a tiny minority component in a universe dominated by mysterious substances that interact with normal matter only through gravity's subtle pull. Standing under tonight's stars, we can reflect that every visible galaxy we see is embedded in a dark matter halo that outweighs its stars by factors of 10 or more. The space between galaxies isn't empty. It's filled with dark energy that pushes space apart faster and faster as time progresses. We live in a universe that's more alien and mysterious than any science fiction writer ever imagined, where the familiar world of atoms and electromagnetic radiation represents just the visible tip of a cosmic iceberg whose bulk remains hidden in darkness. The search for dark matter and dark energy represents the greatest detective story in science, where the criminals outweigh the witnesses by 20 to 1, and the evidence consists of gravitational fingerprints left on visible matter. We're cosmic forensic investigators, gathering clues about substances we've never directly observed, solving a case where understanding the perpetrators might reveal the ultimate fate of everything we can see. For over 50 years, physicists dreamed of detecting gravitational waves, ripples in space-time itself, predicted by Einstein's general relativity, but never directly observed. The challenge seemed impossible. These waves stretch and squeeze space by distances smaller than an atomic nucleus, while traveling at the speed of light across cosmic distances. Building a detector sensitive enough to catch such infinitesimal distortions was like trying to hear a whisper from across the universe while standing next to a thunderstorm. The quest began in the 1960s when Joseph Weber at the University of Maryland built the first gravitational wave detectors, massive aluminum cylinders that should ring like bells if gravitational waves passed through them. Weber claimed to detect signals, but other physicists couldn't reproduce his results. The field entered a period of skepticism and slow, methodical development that would last decades. LIGO, the Laser Interferometer Gravitational Wave Observatory, represented the culmination of 40 years of technological development and over $1 billion of investment. Two identical facilities, one in Livingston, Louisiana, and another in Hanford, Washington, bounce laser beams down 4-kilometer arms arranged in an L shape. If a gravitational wave passes through the detector, one arm stretches while the other compresses by a distance 10,000 times smaller than a proton's width, 1/10,000th the diameter of an atomic nucleus. The engineering challenges were staggering. LIGO's mirrors must be isolated from every conceivable vibration source, from earthquakes and ocean waves to passing trucks, and even the thermal motion of molecules in the mirror material itself. The entire detector operates in ultra-high vacuum to prevent air molecules from disturbing the laser beams. The mirrors are suspended from multi-stage pendulum systems that filter out vibrations while allowing the mirrors to move freely in response to gravitational waves. Even with all these precautions, LIGO must distinguish gravitational wave signals from noise sources that can mimic the effects of space-time distortions. Logging trucks passing near the facility, aircraft flying overhead, storms hundreds of miles away, and even people walking near the buildings can create spurious signals that must be identified and removed from the data. On September 14, 2015, at exactly 9:51, Coordinated Universal Time, both LIGO detectors registered an identical signal. The gravitational waves swept first through the Livingston detector, then reached Hanford 7 milliseconds later, exactly the light travel time between the two facilities. After decades of searching, humanity had finally heard the universe speaking in its most fundamental language. Here's what's really happening. 1.3 billion years ago, two black holes each, about 30 times more massive than our Sun, completed their final death spiral. In the last fraction of a second before collision, they orbited each other at nearly half the speed of light. The merger converted 3 solar masses worth of matter into pure gravitational radiation, releasing more power than all the stars in the observable universe combined, but only for 0.2 of a second. The signal, designated GW150914, appeared in the data as a characteristic chirp, a rapid increase in frequency and amplitude as the black holes spiraled inward faster and faster before merging into a single, more massive black hole. The entire detectable signal lasted only 1/5 of a second, but it carried information that no electromagnetic telescope could ever provide. Gravitational waves revealed the black hole's masses, spins, and orbital dynamics with extraordinary precision. The waves showed that the black holes were spinning in different directions relative to their orbital motion, indicating a violent formation history that had disrupted their initial alignment. The final merged black hole weighed about 62 solar masses, 3 solar masses less than the sum of its constituents, with the missing mass converted entirely into gravitational wave energy, according to Einstein's famous equation E equals mc squared. The discovery opened an entirely new sensory channel for exploring the universe. Gravitational waves carry information that light cannot provide, revealing the dynamics of space-time itself during the universe's most extreme events. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through everything virtually unimpeded, carrying pristine information from the interiors of cosmic catastrophes, LIGO's success triggered a revolution in multi-messenger astronomy. The Virgo detector in Italy joined LIGO in 2017, providing a third gravitational wave antenna that dramatically improved the ability to locate signals in the sky. Additional detectors under construction in Japan and India will create a global network capable of pinpointing gravitational wave sources with extraordinary precision. On August 17, 2017, LIGO and Virgo detected gravitational waves from an entirely different type of cosmic collision, the merger of two neutron stars. Unlike black hole mergers, which produce only gravitational waves, neutron star collisions generate electromagnetic radiation across the entire spectrum, from gamma rays to radio waves. Within seconds of the gravitational wave detection, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same region of sky. Ground-based telescopes around the world swung into action, racing to find the optical counterpart of the gravitational wave source. The SWOPE telescope at Las Campanas Observatory in Chile was the first to spot the new light source dubbed a kilonova in the galaxy NGC 4993, 130 million light-years from Earth. This multi-messenger observation answered one of astronomy's most enduring mysteries. Where do the heaviest elements in the universe come from? The kilonova's light showed the characteristic signatures of gold, platinum, uranium, and other elements heavier than iron. Nuclear physicists had long suspected that these elements were forged during neutron star collisions, but GW1 70817 provided the first direct proof. The collision created conditions so extreme they can barely be described in familiar terms. When neutron stars, each containing more mass than our Sun, compressed into a sphere 12 miles across, slam together at significant fractions of light speed, they generate pressures and temperatures that exceed those in atomic bomb explosions by factors of billions. Under these conditions, atomic nuclei are smashed together and built up through rapid neutron capture processes that can't occur anywhere else in the universe. The kilonova ejected roughly 50 Earth masses of newly forged heavy elements into space at speeds exceeding 10% of light speed. This single collision produced more gold than exists in all of Earth's oceans, and more platinum than has ever been mined in human history. The jewelry on your finger, the gold in your electronics, the uranium in nuclear reactors, all were forged in neutron star collisions, similar to the one LIGO detected. Gravitational wave astronomy has revealed a universe far more dynamic and violent than previously imagined. LIGO and Virgo routinely detect black hole mergers involving objects more massive than any black holes ever found through electromagnetic observations. Some merged black holes spin at nearly the maximum rate allowed by Einstein's theory, indicating formation mechanisms that remain poorly understood. The detected black holes often have masses in the range from 20 to 50 times our Sun's mass, larger than most black holes observed in our galaxy through X-ray emissions. This suggests either that massive stars in the early universe could form black holes larger than current stellar evolution models predict, or that some black holes grew through mergers and accretion processes that aren't well understood. Gravitational wave detections have also placed new constraints on fundamental physics. The nearly simultaneous arrival of gravitational waves and gamma rays from the neutron star merger GW170817 proved that gravitational waves travel at exactly the speed of light, confirming a key prediction of Einstein's theory. The observations also showed that the graviton, the hypothetical particle that mediates gravitational interactions, must be massless, or nearly massless, ruling out alternative theories of gravity that predict massive gravitons. Future gravitational wave detectors will probe even deeper into cosmic history. The proposed Laser Interferometer Space Antenna LISA will consist of 3 spacecraft flying in formation 5 million kilometers apart, connected by laser beams that detect gravitational waves from space. Operating beyond Earth's seismic noise, LISA will be sensitive to lower frequency gravitational waves produced by supermassive black hole mergers, white dwarf binaries throughout our galaxy, and possibly even primordial gravitational waves from the early universe. LISA will detect gravitational waves from supermassive black hole mergers out to cosmological distances, revealing how these monsters grew to billions of solar masses in the universe's first billion years. The space-based detector will also observe thousands of white dwarf binary systems in our galaxy, creating a detailed map of stellar remnants and probing the physics of compact object evolution. Even more ambitious is the proposed Einstein telescope, a third-generation ground-based detector that would be built underground in Europe. With arms 10 kilometers long and operating at cryogenic temperatures, the Einstein telescope would be 10 times more sensitive than current LIGO detectors. This sensitivity would allow detection of neutron star and black hole mergers throughout most of the observable universe, potentially observing hundreds of thousands of gravitational wave sources per year. The Einstein telescope could detect gravitational waves from the first black holes that formed in the universe, revealing how these objects grew and merged during the cosmic dark ages before the first stars ignited. The detector might even catch gravitational waves from the inflationary epoch that preceded the Big Bang's hot, dense phase, providing direct evidence for theories about the universe's ultimate origin. Neutrino astronomy has joined gravitational waves in expanding humanity's cosmic senses beyond electromagnetic radiation. Neutrinos are nearly massless particles that interact so weakly with matter they can pass through entire planets without being affected. Every second, trillions of neutrinos from the Sun stream through your body, but the probability of any single neutrino interacting with your atoms is virtually zero. This ghost-like behavior makes neutrinos incredibly difficult to detect, but also makes them ideal cosmic messengers. Unlike light, which can be absorbed or scattered by dust and gas, neutrinos travel unimpeded from the most distant galaxies and the interiors of the most extreme objects. They carry information about nuclear processes in stellar cores, supernova explosions, and high-energy particle interactions that no other messenger can provide. The IceCube Neutrino Observatory transforms 1 cubic kilometer of Antarctic ice into the world's largest particle detector. Buried sensors detect the faint flashes of light produced when high-energy neutrinos occasionally interact with ice molecules. The detector can determine both the energy and arrival direction of neutrinos, allowing astronomers to trace them back to their cosmic sources. In 2017, IceCube detected a high-energy neutrino designated IceCube 1709222A, and immediately alerted telescopes around the world to observe the sky region from which it came. The Fermi Gamma-Ray Space Telescope found that the neutrino's arrival direction coincided with a flaring blazar, a supermassive black hole 4 billion light-years away, shooting a jet of high-energy particles directly toward Earth. This discovery established the first connection between cosmic neutrinos and their astrophysical sources, proving that supermassive black holes can accelerate particles to energies exceeding those produced in any human-made particle accelerator. The blazar TXS 0506+56 was acting as a cosmic particle accelerator, generating neutrinos with energies thousands of times higher than the most energetic particles created in the Large Hadron Collider. Neutrino astronomy has also revolutionized our understanding of stellar explosions. When a massive star explodes as a supernova, 99% of the explosion's energy is carried away by neutrinos rather than light. These neutrinos escape from the star's core hours before the shock wave reaches the surface and produces the optical fireworks that telescopes observe. In 1987, neutrino detectors on Earth caught 24 neutrinos from supernova 1987 A in the Large Magellanic Cloud, the first time neutrinos from an astrophysical source beyond our solar system had ever been detected. These neutrinos arrived 3 hours before optical telescopes saw the supernova's light, confirming theoretical predictions about how massive stars die and providing insights into neutrino properties that laboratory experiments couldn't achieve. Modern neutrino detectors are designed to provide early warning of nearby supernovas by detecting the neutrino burst that precedes the optical explosion. The Supernova Early Warning System, SNEWSO, connects neutrino observatories around the world to issue alerts when multiple detectors simultaneously observe neutrino bursts characteristic of stellar core collapse. Cosmic ray astronomy studies the highest energy particles in the universe. Atomic nuclei accelerated to energies that exceed those in human-made accelerators by factors of millions. These cosmic rays slam into Earth's atmosphere constantly, creating showers of secondary particles that rain down on the surface. The most energetic cosmic rays carry energies equivalent to a baseball traveling at 60 miles per hour, extraordinary for subatomic particles. The Pierre Auger Observatory in Argentina uses an array of detectors spread across 3,000 square kilometers to study the most energetic cosmic rays. When an ultra-high energy cosmic ray hits the atmosphere, it creates a shower of billions of secondary particles that spread across tens of square kilometers. By measuring the arrival times and energies of these particles at multiple detector stations, scientists can reconstruct the original cosmic ray's energy and arrival direction. The most energetic cosmic rays observed by Auger carry energies exceeding 10 to the 20th electron volts, 100 million times more energetic than particles produced in the Large Hadron Collider. These particles possess so much energy that relativistic effects become extreme. They travel at speeds differing from light by less than 1 part in 10 to the 23rd. A cosmic ray proton with this energy has the same kinetic energy as a golf ball traveling at 100 miles per hour, compressed into a single atomic nucleus. The sources of these ultra-high energy cosmic rays remain mysterious. Normal astrophysical acceleration mechanisms, supernova shock waves, pulsar magnetospheres, even supermassive black hole jets struggle to explain particles with such extreme energies. The cosmic rays might come from exotic objects like gamma-ray bursts, magnetars with magnetic fields trillions of times stronger than Earth's, or even more. Speculative sources like decaying dark matter particles or cosmic string interactions. Multi-messenger astronomy's true power emerges when different types of signals arrive from the same cosmic event. The neutron-star merger, GW170817, demonstrated this potential by generating gravitational waves, gamma rays, optical light, infrared radiation, radio waves, and possibly neutrinos, each carrying unique information about different aspects of the collision. The gravitational waves revealed the masses and spins of the neutron stars before collision and provided precise timing for the merger event. The gamma-ray burst showed that at least one neutron star was disrupted, rather than collapsing directly into a black hole. Optical and infrared observations revealed the kilonova powered by radioactive decay of newly synthesized heavy elements. Radio observations tracked the expanding shockwave as it interacted with surrounding gas. Future multi-messenger observations will probe cosmic phenomena with unprecedented detail. When the next nearby supernova explodes, gravitational wave detectors might catch ripples from the collapsing stellar core while neutrino observatories detect the burst of particles escaping from the explosion's heart. Optical telescopes will track the shockwave's emergence, while X-ray and gamma-ray instruments monitor high-energy processes in the expanding fireball. The combination of different messengers allows astronomers to test fundamental physics under extreme conditions impossible to replicate on Earth. Neutron star mergers probe matter at nuclear densities while generating magnetic fields billions of times stronger than any produced in laboratories. Black hole mergers reveal how space-time behaves when curved to its ultimate limits. These observations also provide new ways to measure cosmic distances and test cosmological models. Gravitational wave signals encode information about their sources' distances that doesn't depend on the cosmic distance ladder the chain of measurements astronomers use to establish distances to remote galaxies. Binary neutron star mergers observed in both gravitational waves and electromagnetic radiation provide standard sirens that could resolve debates about the universe's expansion rate. The Hubble constant, which describes how fast the universe expands, has different values when measured using the cosmic microwave background versus observations of nearby supernovas. This Hubble tension might indicate new physics beyond the standard cosmological model, or it could result from systematic errors in one measurement technique. Gravitational wave standard sirens provide an independent method that could resolve this discrepancy. Multi-messenger astronomy has also revealed new classes of cosmic phenomena that remained hidden when observed with only electromagnetic radiation. Fast radio bursts, mysterious millisecond, duration pulses of radio emission were discovered in archived pulsar survey data in 2007. These bursts release as much energy in milliseconds as our Sun produces in days, but their origins remained completely unknown until recently. In 2020, multiple radio telescopes detected a fast radio burst from a magnetar in our own galaxy, the first time such a burst had been localized to a specific astronomical object. Simultaneously, X-ray satellites observed high-energy emissions from the same magnetar, proving that at least some fast radio bursts originate from these ultra-magnetized neutron stars. The discovery connected fast radio bursts to one of the universe's most extreme magnetic environments. Magnetars possess magnetic fields a quadrillion times stronger than Earth's, so intense they would strip electrons from atoms at distances of thousands of kilometers. These fields store enormous amounts of energy that can be suddenly released in magnetic reconnection events, generating the intense radio pulses we observe as fast radio bursts. Cosmic ray observations have identified another mysterious phenomenon. The arrival directions of the highest energy cosmic rays show subtle patterns that suggest they originate from specific regions of the sky, rather than arriving randomly from all directions. These anisotropies point toward the galactic center and other regions containing powerful astrophysical objects, but the correlations are weak enough that individual sources remain unidentified. The combination of cosmic ray directions with gravitational wave and neutrino observations might eventually reveal the sources of these ultra-high energy particles. If cosmic rays are accelerated in the same environments that produce gravitational waves or high-energy neutrinos, multi-messenger observations could solve one of high-energy astrophysics' most enduring puzzles. Future detectors will expand multi-messenger astronomy's reach across cosmic history. The proposed Big Bang Observer would use space-based gravitational wave interferometry to detect primordial gravitational waves from cosmic inflation, the exponential expansion that occurred in the universe's first fraction of a second. These waves would carry information about physics at energy scales far beyond what particle accelerators can probe. Next-generation neutrino telescopes like KM3 in the Mediterranean Sea and the planned IceCube Gen 2 will increase sensitivity to cosmic neutrinos by orders of magnitude. These detectors will observe neutrinos from supernova explosions throughout our galaxy and detect high-energy neutrinos from active galactic nuclei across cosmological distances. Radio astronomy continues evolving toward ever greater sensitivity and broader sky coverage. The square-kilometre array currently under construction in Australia and South Africa will be 50 times more sensitive than current radio telescopes when completed. SKA will detect radio signals from the epoch of reionization, when the first stars and galaxies lit up the universe, and it will search for technosignatures from extraterrestrial civilizations across thousands of nearby star systems. Here's what multi-messenger astronomy means for our understanding of the universe. We're developing the ability to observe cosmic phenomena with all our senses simultaneously, like gaining sight, hearing, touch, and smell, after relying on only one sense throughout human history. Each messenger electromagnetic radiation, gravitational waves, neutrinos, cosmic rays, provides complementary information that reveals different aspects of the same physical processes. Standing under tonight's stars, we can appreciate that invisible messengers are constantly streaming past us from across the cosmos. Gravitational waves from black hole mergers, billions of light years away, are stretching and squeezing space around you by amounts smaller than atomic nuclei. Neutrinos from stellar explosions in distant galaxies are passing through your body every second. Cosmic rays accelerated in supernova shockwaves are colliding with atoms in the upper atmosphere, creating showers of particles that reach the ground. The universe is not just brighter and more diverse than we imagined, it's speaking to us in multiple languages simultaneously. Multi-messenger astronomy has given us the tools to understand these cosmic conversations, revealing a cosmos where the most extreme events leave signatures detectable across multiple types of radiation and particles. Each new messenger discovered has revolutionized our understanding of cosmic phenomena, from pulsars and quasars revealed by radio astronomy to black holes exposed by X-ray observations. Gravitational waves and high-energy neutrinos represent the newest additions to our sensory arsenal, but they certainly won't be the last. Future discoveries might reveal cosmic messengers we haven't yet imagined, opening new windows on the universe's most extreme and exotic phenomena. The cosmic detective story continues to unfold as our instruments become more sensitive and our understanding of fundamental physics evolves. Multi-messenger astronomy ensures that when the next major cosmic discovery occurs, we'll be equipped to observe it from every possible angle, gathering the complete story rather than just scattered clues. The universe's greatest secrets are written in languages we're still learning to read, but each new messenger brings us closer to cosmic literacy. Today's unanswered questions dwarf those that kept ancient astronomers awake under starlit skies. The James Webb Space Telescope peers 13.5 billion years into the cosmic past, capturing light from galaxies that formed when the universe was less than 400 million years old. What it sees shouldn't exist according to our best theories of cosmic evolution. These primordial galaxies are too massive, too mature, too rich in heavy elements for their cosmic age. They contain billions of stars and supermassive black holes that weigh hundreds of millions of solar masses, yet they formed when the universe was barely 3% of its current age. Current models of star formation and galaxy assembly cannot explain how such massive structures assembled so quickly after the Big Bang. Here's what's really happening. Each answer, astronomy provides birth to 10 new mysteries, and our most sophisticated instruments are revealing a universe that consistently refuses to conform to human expectations. Every breakthrough that seems to close one chapter of cosmic understanding opens several new volumes of questions we didn't know existed. Webb has spotted galaxies with redshifts exceeding 13, meaning their light has been stretched by cosmic expansion to wavelengths over 14 times longer than when it was emitted. These ancient systems shine with the luminosity of mature galaxies containing countless stars, yet they formed during what astronomers call the cosmic dark ages, before the first generation of massive stars had time to forge heavy elements and die in supernova explosions. The telescope has discovered that supermassive black holes existed when the universe was only about 600 million years old, enormous gravitational monsters that somehow grew to billions of solar masses in a cosmic instant. Black hole growth requires matter to fall past the event horizon, but there are physical limits to how fast this process can occur. Even if these black holes started as 1,000 solar mass seeds immediately after the Big Bang, they would need to grow at maximum theoretical rates for their entire existence to reach the observed masses. Yet there they are, fully formed cosmic giants lurking in the hearts of infant galaxies. The mystery deepens with Webb's discovery that early galaxies contain surprisingly large amounts of oxygen, carbon, and other heavy elements. These elements can only be produced inside massive stars that live for millions of years before exploding as supernovas. But if the universe was only a few 100 million years old when these galaxies formed, There shouldn't have been enough time for multiple generations of stellar evolution to enrich the interstellar medium with heavy elements. We've also learned that the universe's expansion accelerates due to dark energy, but we have no idea what dark energy actually is. It comprises 68% of everything that exists, yet it might be nothing more than the quantum mechanical energy of empty space itself. Alternative theories propose that dark energy results from extra dimensions, leaking gravitational effects into our three-dimensional reality, or from scalar fields that permeate the cosmos like invisible fluids. The search for dark matter has consumed decades of effort and billions of dollars, yet the mysterious substance continues to evade direct detection. Underground laboratories around the world house increasingly sensitive detectors designed to catch dark matter particles, but each experiment that finds nothing forces physicists to consider ever more exotic possibilities. Perhaps dark matter consists of axions, hypothetical particles, so light and weakly interacting that they're virtually undetectable. Maybe it's composed of sterile neutrinos that interact with normal matter only through gravity. Or it could be something even stranger. Primordial black holes, mirror matter, or particles that exist in hidden sectors of reality we've never imagined. The cosmic web itself poses profound puzzles. This largest-scale structure in the universe consists of dark matter filaments stretching across billions of light-years, connecting galaxy clusters like a three-dimensional spider web, spanning observable space. Computer simulations can reproduce the web's basic architecture, but they struggle to explain many observed details. Why do some filaments contain more galaxies than others? How do supermassive black holes coordinate their growth across cosmic distances? What determines which intersections of the cosmic web become rich galaxy clusters versus sparse groups? Galaxy formation remains one of astronomy's most challenging unsolved problems. We know that galaxies form within dark matter halos through processes involving gas, cooling, star formation, and feedback from stellar explosions and supermassive black holes. But the details resist understanding despite decades of increasingly sophisticated computer simulations. Why do galaxies have the masses, sizes, and star formation rates we observe? What determines whether a dark matter halo will host a spiral galaxy, an elliptical galaxy, or remain essentially empty? The relationship between galaxies and their central black holes presents another cosmic puzzle. Nearly every massive galaxy contains a supermassive black hole whose mass correlates tightly with the galaxy's central stellar bulge. This relationship holds across 5 orders of magnitude in black hole mass, from millions to tens of billions of solar masses. Yet the black holes are thousands of times smaller than their host galaxies, raising profound questions about how such distant objects can influence each other's growth. Some process must coordinate black hole and galaxy evolution across vast differences in scale and timescale. Black holes can grow rapidly through accretion, while galaxy assembly occurs through mergers and gradual gas accretion, spanning billions of years. How do these disparate processes remain synchronized? What feedback mechanisms regulate both star formation and black hole growth simultaneously? The search for extraterrestrial life has become one of astronomy's most compelling frontiers, driven by the discovery that planets orbit virtually every star in the galaxy. Conservative estimates suggest our galaxy contains at least 40 billion potentially habitable worlds, planets orbiting in the temperature zones where liquid water can exist on planetary surfaces. The numbers alone suggest we shouldn't be alone, yet the cosmos remains silent to our increasingly sophisticated searches. This silence poses the Fermi paradox in stark terms. If life is common and some civilizations develop interstellar technology, why haven't we detected any evidence of their existence? Perhaps life is far rarer than optimistic estimates suggest. Maybe intelligence is an unlikely evolutionary outcome, or technological civilizations tend to destroy themselves before achieving interstellar communication. Alternatively, advanced civilizations might use communication methods we haven't discovered, or they might be deliberately avoiding contact with younger species like ourselves. The paradox deepens with each exoplanet discovery. The TRAPPIST-1 system contains 7 Earth-sized worlds, 3 orbiting in the habitable zone around a nearby red dwarf star. Proxima Centauri b sits in the habitable zone of our closest stellar neighbor. Kepler's surveys revealed that roughly 1 in 5 Sun-like stars hosts Earth-sized planets in temperate orbits. If even a tiny fraction of these worlds developed life, and if even a microscopic fraction of those developed intelligence, our galaxy should teem with technological civilizations. Yet our radio telescopes detect only cosmic static punctuated by the occasional natural pulsar signal. New questions emerge as our instruments become more sophisticated. The Event Horizon Telescope has imaged the shadows of supermassive black holes in the centers of the Milky Way and the galaxy M87, revealing the silhouettes of objects so massive that they bend light around themselves like cosmic funhouse mirrors. These images confirm Einstein's predictions about how black holes warp space-time, but they also reveal unexpected details about how matter behaves in the strongest gravitational fields in the universe. M87's black hole launches a jet of plasma thousands of light-years into space at nearly the speed of light. This jet contains more energy than could be generated by converting the entire mass of our Sun into pure energy every single day for millions of years. We can observe this cosmic violence in exquisite detail, but we still don't understand the physical mechanisms that accelerate particles to such extreme velocities or collimate them into narrow beams across such vast distances. Gravitational wave astronomy has revealed black hole populations that weren't predicted by stellar evolution models. The black holes detected by LIGO often have masses in the range of 20 to 50 solar masses, larger than most black holes found through X-ray observations in our galaxy. Some of these objects might form through entirely different mechanisms than standard stellar collapse, perhaps involving the direct collapse of primordial gas clouds in the early universe, or the merger of smaller black holes in dense stellar clusters, the most energetic events ever observed gamma ray. Bursts remain partially mysterious despite decades of study. We know they're produced by the collapse of extremely massive stars, or the merger of neutron stars, but the details of how they generate such enormous energies continue to challenge theoretical understanding. A single gamma-ray burst can release more energy in 10 seconds than our Sun will produce in its entire 10 billion-year lifetime. Yet this energy emerges from regions smaller than Earth's orbit around the Sunday. Fast radio bursts represent an entirely new class of cosmic phenomena discovered just over a decade ago. These millisecond duration pulses of radio emission release as much energy as our Sun produces in days, but they occur in time intervals shorter than human heartbeats. Most fast radio bursts have been detected from distant galaxies, billions of light-years away, but astronomers have identified only a handful of the objects responsible for producing them. The cosmic acceleration discovered through supernova observations in 1998 has led to predictions about the universe's far future that border on the fantastic. If dark energy continues to drive accelerating expansion, the observable universe will eventually become a lonely place. Galaxy clusters will be pushed apart until each becomes isolated in its own expanding bubble of space. Even the local group containing the Milky Way and Andromeda galaxies will eventually be stretched apart, leaving each galaxy alone in the cosmic dark. Eventually, star formation will cease as galaxies exhaust their gas supplies and can no longer accrete fresh material from the increasingly tenuous intergalactic medium. Existing stars will age and die, leaving behind white dwarfs, neutron stars, and black holes as the last remnants of stellar evolution. The universe will enter what cosmologists call the degenerate era, when only the longest-lived objects remain to mark the passage of cosmic time. Even this isn't the end. Quantum mechanical and processes will eventually cause protons themselves to decay, dissolving the atomic nuclei that comprise normal matter. White dwarf stars will slowly evaporate as their constituent particles decay, leaving only black holes as the last massive objects in an expanding, cooling cosmos. Finally, even black holes will evaporate through Hawking radiation, returning their mass to the vacuum as elementary particles that will be stretched across ever larger volumes by the relentless expansion of space. Yet these predictions assume that dark energy remains constant throughout cosmic time. We have no guarantee that this assumption is correct. Dark energy might decay, reversing cosmic acceleration and causing the universe to collapse in a big crunch. Alternatively, dark energy might strengthen, leading to a big rip scenario where acceleration becomes so intense that it tears apart galaxies, stars, planets, and eventually atoms themselves. Future observatories will probe these cosmic mysteries with unprecedented power and precision. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters across, larger than a basketball court. This enormous light-collecting area will enable direct imaging of exoplanet atmospheres around nearby stars, potentially detecting biosignatures like oxygen and water vapor that might indicate the presence of life. The Roman Space Telescope will survey hundreds of millions of galaxies to map dark matter's distribution throughout the universe and trace dark energy's effects on cosmic structure formation. The telescope will also conduct the most comprehensive census of exoplanets ever attempted, using gravitational microlensing to detect Earth-mass worlds orbiting at distances similar to our planet's orbit around the Sun. Ground-based gravitational wave detectors are being upgraded to increase their sensitivity by factors of 10 or more. These improvements will enable detection of neutron star and black hole mergers throughout most of the observable universe, potentially observing thousands of gravitational wave sources per year. The data will reveal how black holes and neutron stars form and evolve across cosmic time, providing new insights into stellar evolution and the physics of matter under extreme conditions. The proposed laser interferometer space antenna will detect gravitational waves from space, observing lower frequency signals that Earth-based detectors cannot access. LISA will watch supermassive black holes merge as galaxies collide, revealing how these cosmic monsters grow and influence their host galaxies' evolution. The space-based detector might even catch gravitational waves from the inflationary epoch that preceded the Big Bang's hot, dense phase. Neutrino astronomy will expand dramatically, with next-generation detectors that use volumes of water or ice measured in cubic kilometers. These enormous observatories will detect neutrinos from supernova explosions throughout our galaxy, and high-energy neutrinos from active galactic nuclei across cosmological distances. The observations will reveal how matter behaves in the most extreme environments in the universe and provide new insights into the fundamental properties of neutrinos themselves. Radio astronomy continues evolving toward telescopes that will survey the entire sky continuously, monitoring millions of sources for variability and transient events. The square-kilometer array will be sensitive enough to detect radio leakage from technological civilizations around nearby stars, potentially answering the question of whether we're alone in the universe. The telescope will also observe hydrogen gas in the most distant galaxies, tracing star formation back to the cosmic dark ages when the first stars ignited. Perhaps most tantalizingly, future experiments might detect dark matter directly for the first time. Next-generation underground detectors will be sensitive enough to catch even DVAN, the rarest interactions between dark matter particles and atomic nuclei. Space-based detectors will search for dark matter annihilation signatures in gamma rays and positrons. Particle accelerators might create dark matter particles in high-energy collisions, finally revealing the nature of the universe's most abundant form of matter. Yet for every question these future observations answer, they will undoubtedly reveal new mysteries we can't currently imagine. The history of astronomy teaches us that the universe consistently exceeds human expectations, presenting phenomena more exotic and wonderful than our theories predict. Each generation of astronomers believes they're approaching a complete understanding of cosmic reality, only to discover that they've been examining a small fragment of a far grander and stranger picture. The questions that burned in ancient minds as they watched wandering stars have evolved into investigations of dark matter, dark energy, gravitational waves, and the search for life among billions of exoplanets. But the fundamental drive remains unchanged. We are a species compelled to understand our place in the cosmos, to transform mystery into knowledge, to find meaning in the vast scales and deep time that dwarf human experience. Standing under tonight's stars, we can appreciate that we live during a unique moment in cosmic history. The universe is old enough for complex structures to have formed galaxies, stars, planets, and life itself, yet young enough that we can still observe the cosmic microwave background radiation from its birth. We exist in a brief epoch when both dark matter and dark energy significantly influence cosmic evolution, when we can detect gravitational waves from black hole mergers and observe light from the most distant galaxies. Future generations might inhabit a universe where accelerating expansion has pushed distant galaxies beyond observation, leaving only the local group visible in the night sky. Or they might discover technologies and physical principles that reveal the cosmos as even stranger and more wonderful than we currently imagine. They will certainly face questions we haven't yet learned to ask, probing phenomena that exist beyond our current conceptual frameworks. The night sky remains what it has always been, an infinite invitation to wonder, written in languages we're still learning to read. Every photon that reaches our telescopes, every gravitational wave that stretches our detectors, every neutrino that passes through our instruments, carries messages from cosmic realms that challenge human imagination. The darkness between stars continues to hold secrets about the nature of space, time, matter, and the ultimate fate of everything we can observe. We are cosmic archaeologists deciphering the history written in starlight and space-time distortions. We are time travelers, observing the universe's past through the messages that take billions of years to reach us. We are cosmic cartographers, mapping the distribution of matter and energy across scales that span from subatomic particles to the largest structures in space. Most profoundly, we are questioners, inheritors of the curiosity that first stirred in ancient minds watching those 5 wandering stars against the cosmic dark. The questions without end ensure that the universe will continue surprising us, challenging us, and inspiring us to reach beyond the boundaries of current understanding toward truths we can barely glimpse from our small, warm planet orbiting an ordinary star in an unremarkable galaxy among billions scattered across the observable cosmos.